Right. So we got the quiz, and we are going to get this started. This party started. Thank you for showing up and participating in this circuit breaker basics class. We're going to be covering circuit breakers. We're going to understand how they operate and function, and all the great things that help them do what they do best. And I think hopefully I'll help. I will be talking National Electrical Code requirements, some of the areas in the NEC that are impacted by that impact circuit breakers and their application and are important to their proper application. I'll also be relating some of the stuff that we're going to talk about to electrical safe work practices as well, because there's a lot of things about molded case, insulated case, and power circuit breakers that offer a lot to the electrical worker that we need to understand and leverage as best we can in the power distribution. So as usual, for those of you who have been with me on this journey from all of last week and into this week now, here on Thursday, we're skipping tomorrow for Good Friday, and then Monday we're going to start up on NEC code changes again. But we do a quiz, and I sent this anonymous quiz out, and we got pretty good response. And we're going to go over the questions and answers now, and here we go. So the first question was, if not labeled with an interrupting rating, what is the assumed interrupting rating of a molded case circuit breaker? 2,000, 5,000, or 10,000, 22,000, or I haven't a clue. And the right answer on this one here is 5,000 amps. We're going to go over the section of the NEC that covers that, but that's an important thing to remember. So we're going to cover the details of that as we go through the slide deck. So that was a good one. 270 people responding. Thank you very much. Let's move to the next question. A miniature circuit breaker is a UL listed molded case circuit breaker specifically made for residential market per the standard. 61 true, 146 false, 41 not sure, and then 7 option 4s. So I don't, I made this pretty late last night. So in any case, when we say use the term miniature circuit breaker, that is really an industry term. That's not something that's in the National Electrical Code. It's not something in the UL standards. It's something that product manufacturers use to designate different product lines. Another good example of that would be load center. We use the term load center for residential applications as opposed to a panel board, which they would expect to see in industrial and commercial systems. A load center is a panel board. It's listed to the same standard as panel boards, but when we say load center and we use terms like miniature circuit breaker and even insulated case circuit breakers, those are all separate types of things that the industry uses as terminology, but it's not necessarily in the standard. So the answer to this one is false. 153 of you did a great job. Thanks for responding. I love the engagement, 268 people. And if you go to menti.com and use this code 226896, you can actively just walk through and contribute your perspectives. It's great to see where we are starting from. This helps me understand what level of detail I need to go into and where. The interrupting rating of a circuit breaker is compared with the symmetrical, asymmetrical, peak, or not sure, throw me a bone here, short circuit current value. So the interrupting rating, we calculate symmetrical RMS amps when we do our short circuit studies. So 129 of you now, 130, now that you guys hear the right answer, you're all piling on. That's okay. That's good. 130 of you guys now are correct. We will do the evaluations of interrupting ratings based upon symmetrical amps, but I'm going to teach you during this program that we need to learn about the X to R ratio and the asymmetrical, because when we test a circuit breaker, we will test it with what we think is probably the worst case circuit configuration, which has to do with how much inductance versus reactance that we have in the system. That dictates the phase sequencing of the waveforms in the from a current to voltage perspective. I'm going to show you that and help you understand how we test a circuit breaker and whenever you apply these devices, what to look for to know whether or not you may have to derate, or you may need to call somebody to get some further information. The interrupting rating of a circuit breaker is generally determined on the basis of line-to-line fault, symmetrical fault current, single line to ground, or double line to ground. And the right answer to that one, again, is the big red bar there, symmetrical fault current, just based on the last answer as well. What we get into here is whenever we calculate fault currents, and I covered this 2 Mondays ago, and it's up on my YouTube channel, the entire 2-hour session on short circuits. We talked about all the different types of short circuit values that we'll calculate. Call in user 20. Remember to mute. We talked about this in that session that basically whenever you calculate fault currents, we'll calculate line to line, 3-phase bolted fault current values. We'll do line to ground short circuit, ground fault currents, all these different ways and fault currents that we will calculate, and we do that for different reasons. Call in user 20. Need you to mute. And I don't see you on here. Let me find you. I'm going to find call in user 20. Give me a second. There you are. Call in user 20. I'm muting you. You done been muted. So, whoops. So we talked about all the different types of fault currents, and there's reasons you'll calculate different fault currents in the system to understand how overcurrent devices may function and operate. But when we talk about the interrupting rating, we're looking at that line symmetrical 3-phase bolted fault current, or whatever that symmetrical highest fault current is. It could be the line to ground fault. An AC circuit breaker can be used on DC when you derate the interrupting rating by 80%, when all poles are used in series and you derate by 80%, no one is watching. 10 people said when no one's watching. You know what? Those are the 10 people that go down that road and they don't see the cops, right? And they put their foot on the gas, and then when they see the cop, they let it off. All right. The time constant of the DC system is within the listing. Now, I think that 39, they were guessing. I mean, because I just made that up. Okay. You guys are wrong, and so is those when no one's watching. And then the 7 that doesn't know what a circuit breaker is, we're going to teach you that. But none of the above is the right answer, because you can't. The only way you can use a breaker that's listed for AC is when it's also listed for DC. Okay, you have to have circuit breakers that are listed for the application, and we'll talk a little bit more about that on how we get that done. But remember, AC current is a lot different than DC. What's the big thing that's missing? 0 crossings. Circuit breakers and fuses love 0 crossings. They eat them up. That's when we do our best in stopping that flow of current. So the right answer, 127 of you out of 268, 129 of you out of 269. Got that one right. And look, it just keeps going up. A thermomagnetic circuit breaker will protect all installed wires and connected cords. 84 said true, 157 said false, 13 have no clue. Those who are in the false column, that is correct. A thermomagnetic circuit breaker is designed to protect the wire that's connected to it. Once you get to connected cords, if you think about it, just think about whatever it is that you're plugging in. Look at the cord that you're plugging in. I'm looking for a cord around here. I can't find one. Wireless. If you look at the cord that you're plugging in, it's not, I mean, if you have a 20 amp circuit, that cord you're plugging into that receptacle is not 20 amps worth of conductor. It's much smaller. And if you really read 240, Article 240 in the National Electrical Code, it tells you that most of those connected cords are really the protection from a thermal, etc. capability are protected based upon the listing. So if I use a product and I have the right cord for that product as per its listing, I will be using it within its parameters of listing, and that's what's going to provide a level of protection for it. Now, what we learned over time, and what we'll talk about a little bit, we had a class last week on, is the arc fault circuit interrupter that basically looks for damaged in those conductors, arcing and sparking that can cause fires. And that technology can extend and and it basically lowers some thresholds. We're looking at signatures and can provide protection for those conductors, those connected cords. But in reality, those breakers are protecting the conductors that are behind the walls, the conductors that are connected to it. That's what it's there to protect, not those cords that we plug into the wall. And so false. The answer is false. U86, we love you. That's why I'm here. 240-volt circuit breakers applied on a 40-volt system will self-destruct if turned on. True or false? And those who said 197 said false. That is correct. They will not. And that's part of the issue. Even if you exceed the interrupting rating, where you apply a circuit breaker that, or a fuse, it doesn't really matter, where the available fault current is greater than its interrupting rating, everything will work just fine until it's called to act. The moment that device has to do its job, that is when you are going to, or could possibly have a problem where it may, what we call, and Dan Neeser lovingly refers it to, an unintended rapid disassembly in the field, right? It could cause an issue, very well could be an issue itself. So no, it won't self-destruct. It'll turn on, it'll supply power until it's called to do something. Sort of like me. I'm really good on the couch until you ask me to do something. Circuit breakers are not current limiting, only fuses are. 83 said true, 168 said false, and 7 are looking for the dessert table. That's fine. You 7, keep on looking, but watch this video because the right answer to this is false. There are current limiting circuit breakers. Remember, circuit breakers and fuses, both, you can have current limiting devices. What you're looking for on the label, it'll have to say, based on the UL standards, they have to tell you that it's current limiting. And then once it's current limiting, you have all of this other information available for you. You have let-through charts, you have the diagrams, you have their I2T let-through information. You have a lot of really important information that can be strategically used to help protect equipment. All right. Motor circuit protectors can be used to protect a branch circuit. 82 said true, 661 said false, and 15 aren't sure. They're probably still over there at that dessert table. Remember that, and we'll talk a little bit about this as well, motor circuit protectors don't have a thermal overload portion of the trip characteristics. And I need that thermal to protect conductors from overheating. So I can't use a motor circuit protector to protect a branch circuit because they don't have thermal overload protection. Where you will see a motor circuit protector is in a motor control bucket, motor control center bucket, something in a starter type of perspective. They are recognized components of an assembly that we assume that you will have thermal overload elements as part of that motor control circuit that does the overload protection. A motor circuit protection has instantaneous only, and it provides short circuit protection. So that's an important distinction, and we can't forget. You know, they look the same. You know, they'll look. You just got to read the labels and understand that there's some parts not in that circuit breaker that are important to protecting conductors. Only molded case circuit breakers from the same manufacturer of the panel can be used together. 72 said true, 178 said false, and we got some of the guys back from the dessert table. Thank you very much. They're back in the game. Not that they were right on this, I don't know, but 180 got this right. When you have a product that is classified and listed as a classified device, you do have to be careful that you don't use my breaker in someone else's panel if you're not using a classified device, and you can't use someone else's breaker in my panels if you're not using a classified device that's listed and tested for use in that panel board. And what you'll see with a classified circuit breaker program, they will provide all of the catalog numbers of panel boards that circuit breaker is permitted to be placed in. Now, the value of a circuit breaker like that, it's really prevalent in the residential and light commercial market, where you have a truck and you're going out to a job site and you need a circuit breaker to go into a panel board, and maybe it's not the brand that you thought it was going to be when you showed up. Our classified breaker can be placed in some of those panels. They're listed for that. We test it for that. So that can help reduce the number of circuit breakers that you have on the truck. So that program's been around for quite some time, and I think it's been leveraged by a lot of people in the industry. So you cannot apply a 90-degree C conductor on a molded case circuit breaker. 179 of you said false, and that is right. We got more people over there at the cake table, though. So the key thing here's the big mistake I always see is people will apply a 90-degree C rated conductor, and they'll use its 90-degree C ampacity. So you can land a 90-degree C conductor on a circuit breaker where the lugs and that equipment is only rated for 75-degree C. But you still have to use the 75-degree C column when you determine as a limiting factor, right? So when you think about conductor ampacity, we have to first consider the conditions of use and go through 240, calculate it where you assume 85% of continuous loads and et cetera, and then you do the same thing where you don't consider that, but you look at another aspect of the parameter. So you're going to do that evaluation and then make sure that whatever you're landing on it, if it's a 75-degree C or 60, you have to use that. Maybe your termination may be the limiting factor of how much current you can draw through that conductor. So the answer to this one is you can use a 90-degree C conductor. You just can't use the 90-degree C ampacity. Okay? Follow the rules on sizing and determining the ampacity of the conductor. You can use 90-degree C to determine the ampacity, but you just can't use the 90-degree C when you have to consider the 75-degree C rating of the equipment that you're landing in. All right, so that was the quiz. I didn't miss it. Thank you for reminding me. We had a few people. I scolded everybody yesterday because I got like halfway through the program and I didn't go through the quiz. So that's the name of that tune. All right, we're still streaming. We're still streaming on YouTube. We got, let's see how many people we got. Let's take a look and see if we got any questions and check out how many people we have out there on YouTube land. My tubers. We got about 238. Let's take a look. It's just that now the results are coming in live along with Thomas on the video. Excellent. Gabe Paletti, thanks for joining us. Gabe. Brian Kroger, the bottom 1/3 is all black. I don't remember it doing that Fast Tuesdays when it exits out of Menti. All right. Well. Yeah, you know why? Here, I'll fix that for you guys. Watch this. Watch this. Here's we go. Control 3 and Control Q, and boom. You're seeing the whole screen now. So my YouTubers, let's take a look on Facebook. All right, we're doing good on Facebook. YouTube, let's take a look at our chat session over here on WebEx, see what kind of questions or comments we've got going on. I see this thing scrolling. I got to keep it out of my eye. The circuit out to the motor is a branch circuit. Yes. But that motor circuit protector, the MCP, is not a branch circuit protected device. It has to work in combination with the starter and the overload. Right? The starter has the overload protection. Perfect, Eddie. Do all or most fuses and circuit breakers have some degree of intrinsic current limitation due to internal contact? So David Shapiro. So yes. So here's the thing. Current limitation. I would say that current limitation is definitely a most of your circuit breakers, most of your what do you call it, molded case circuit breakers and some of your insulated case. When you get into the insulated case and your power breakers, now you've got intentional delays. Your molded case circuit breakers, at some point, they're all going to be current limiting for the most part. The key thing is you can't really claim that unless you list it that way. So that's an important thing. I can't really take advantage of current limitation unless I have it listed as a current limiting device, and then I have a lot of information provided. I've always heard them called motor feeders. So why are MCCBs rated for 75 C? Does the thermal aspect trip above that? So Krista Ross, So good question. Molded case circuit breakers, here's the hardest test for a molded case circuit breaker to pass: heat rise. What they do in a heat rise test is you put the circuit breaker in your enclosure, you put temperature probes in different locations on that circuit breaker, and you run current through it. You go through a defined process in UL 489. You can't exceed a certain heat rise within that box. It impacts a lot of different things with regard to the proper operation of the device and whatnot. So you're not allowed to exceed that temperature rise, and 75 degrees C is that number that we have for a lot of different pieces of equipment. So it all has to do about the thermal capabilities of these devices and the heat that's in the box. You got to get the heat out. And we use the copper, that conductor, to help draw the heat away from the overcurrent protective device, and it's around the it's around those terminations and the device itself. So you don't want to get everything too hot in there. Heat's ungood for a breaker or a fuse. 430 part 4 motor branch circuit, Alan Gibbons. So I guess 90 degrees C is for the derating of a conductor for ambient temperature or conduit feel. Yes. Kevin Ryan. WebEx chat is showing questions twice. Really? Interesting. Could you provide answers to the test for the ones who joined later? Yes, I can. You know what I'll do? And I think what I'll do is I'll go back through my previous quizzes and I'll just write up the questions for all of those quizzes and send them out. I'll put those out there. What is the ambient temperature when testing? That's a good question, Adam. I'd have to pull up the standard. I believe they just go by room temperature. I can't remember the exact number, the range, but it's in the standard. If I have time, I'll go pull that standard. If not, I'll try to answer that later. All right. So let's, you're welcome, Adam. All of your phones, again, have been muted. I think everybody gets that right now. Please watch. WebEx is the only area that I have to worry about. I don't have to worry about Facebook or YouTube. All right, so, and I have to say that, again, I may be a member of various committees. I do not speak on behalf of those committees. I do not speak on behalf of NFPA or Codemaking Panel 2 or Codemaking Panel 10, of which I'm a member, or 70B, or any of the other committees. Everything you hear is my opinion, and I rely on those on chat to keep chatting and let me know when I misspeak. This is... it's kind of confusing when you're trying to run 13 or 14 different things at the same time. So please, keep chatting it up. Correct me if you think I'm wrong, and we'll have the dialogue. All right. So that's all I have to say about that. IEI, great organization. NFPA, IEEE, 3 organizations I belong to that shaped who I am today, I think, and built my network of individuals. So please, keep those organizations near and dear to your heart, and engage. They offer opportunities to engage. So, circuit breaker basics. Oops, I just heard somebody. Please mute, unless you have something great to say that everybody's going to benefit from. All right. Circuit breakers. They're defined in Article 100 of the National Electrical Code. The key thing around a circuit breaker is they open the circuit automatically based upon how much current flows through them, and they can be reset. You can turn them on and off. If you're more familiar with fuses, then you think of the circuit breaker as the overcurrent device and the switch together. So that's your circuit breaker and how it functions and operates. Seeing you in a smaller version of the slide is much more gooder. Thank you, Ryan. Jeez. To confirm that software does not calculate arc flash using limiting characteristics. Okay, so Hensel, I don't know if that's a question. I'm not looking at the dialogue, but there was a discussion going on YouTube with regard to arc flash. You can use what they call fuse and circuit breaker equations. The fuse equations leverage the current limiting capabilities of the overcurrent protective device. You can turn that on and off in most of the software packages that I've seen. Okay. Circuit breakers. Now, there's more definitions in Article 100. We have adjustable circuit breakers as apply, and instantaneous trip. We have inverse time. The higher the current, the faster the trip. The lower the current, the longer the trip. That's an important fundamental principle to think about because the incident energy, if I have arcing currents that are lower, they'll be in the longer clearing time, and that will cause higher incident energy. So inverse time is very critical, and we're going to talk about that as we look at time current characteristic curves. Non-adjustable, and then you have adjustable and non-adjustable. So it's key to remember, like a standard thermomagnetic breaker is something that's not adjustable. So if I take a look at your standard residential type of circuit breakers, there's the handle says on this one 15 amps. It's 15 amps. It's not going to change. You're not going to change the thermal pickup. You're not going to make it a 20 amp. You're not going to make the instantaneous change. Now, when you look at some of the larger breakers, they'll have dials on the front of them that have the instantaneous. I may be able to change instantaneous. I may be able to change the long time pickup, short time pickup. And if you don't know what those are, stay here because we're going to teach you. And I can adjust what the capabilities of those circuit breakers are. And that would be your small thermomag breakers. On the larger breakers, we actually have trip units, which we'll cover, that have a lot more functions and features. Let's see, non-adjustable, we talked about that, adjustable, and then settings. Molded, there are three basic types of a circuit breaker. You have molded case, insulated case, and then you have your low voltage power circuit breakers. Those are your big boys, right? And the key difference between these, people ask me, like on some of these, I can get a molded case circuit breaker that's 600 amps. I can get an insulated case circuit breaker that's 600 amps. And this is an insulated case circuit breaker I'm not going to be able to pick up myself. At least Eaton wouldn't let me. I could probably try, I think, if I, to show off some muscles or something. But no, the insulated case is really heavy. Low voltage power circuit breaker is really heavy. But I can get them all in 600 amps. And someone would say, well, why would I buy a low voltage power circuit breaker, which requires a huge big gray box to put it in at 600 amps, rather than a nice small molded case circuit breaker at 600 amps that I could hold in my hand? Why would I do that? And the reason is I can hold my contacts closed longer on that low voltage power circuit breaker for higher fault currents. And then you have to ask yourself, why would I want to hold my contacts closed longer on a 600 amp circuit? I may need that for selective coordination reasons to make sure that a downstream device clears those high fault currents first. I may need that to let some motors start. I may have, like, say, arcing furnaces and things of that nature that are going to draw a lot of current that I have to make sure that my breakers don't open on. As you move up, it's really, in my mind, I relate all of these to the time current characteristic curve. I mean, when you talk about a circuit breaker, I'm picturing a curve in my mind because each of these will have intentional delays and on purpose hold those contacts closed. So we have a question: does adding a molded case breaker inside a pad-mounted distribution transformer constitute refurbishment or modification and void the UL listing? All right, Nathan. If you add a molded case circuit breaker into a piece of equipment, you will probably need to get a field evaluation if it's not listed for that application. Now, we sell dry type transformers with built-in circuit breakers, but the key thing there is going to be, remember we had the 75 C discussion. Heat is not your friend, my friend. Heat is not your friend. So when you start to pack, you put an overcurrent device in there, and you don't have enough heat dissipation, you could create an issue. So when you look at our transformers are listed, and we've tested them with the circuit breakers built in, those devices and that assembly was listed and tested, and we understand the heat rise, and we know we can pass those heat rise tests and things of that nature. If you start modifying products in the field, you're probably going to need a UL field evaluation, either UL or some other nerdle, electro ETL, or one of those Intertex or one of those others, TUV, TUD, Sud Ryland or whatnot. Any one of those nationally recognized testing laboratories that do that. But my guess would be they're going to look at what you're doing and say, that's ungood. So, but yeah, so Nathan, you wouldn't want to just do that in the field. Talk to the manufacturers. There's options for you. What are the major differences between molded case circuit breakers and insulated case circuit breakers? The is none. Right. So a molded case circuit breaker, an insulated case circuit breaker is listed to the same standard as a molded case circuit breaker. Now, here's the big difference. An insulated case circuit breaker is a bigger boy, is a bigger product that has different springs, so I can hold my contacts closed. It's sort of the insulated case circuit breaker was born out of a need to have something between a molded case and a power breaker. I can hold my contacts closed longer. I can provide more short time delay to let downstream devices without bumping right into a low voltage power circuit breaker that's going to be in a low voltage power assembly. I can now have a smaller assembly like a switchboard. I can put an insulated case circuit breakers in there and molded case circuit breakers mixed in that same switchboard, so I can reduce the footprint of my assembly and still provide the delay that's needed that I can't get out of a molded case, because all molded case circuit breakers are going to have an instantaneous pickup that's going to cause them to trip, and they're typically the instantaneous pickup is not a UL 489 requirement. I am not required to have a circuit breaker with an instantaneous. The instantaneous pickup is there. It is put there by the manufacturer so that we protect the breaker from unintended rapid disassembly, because the hardest thing for a breaker is to hold those contacts closed while all of those magnetic forces want to blow them apart. So what we want to avoid is chatter. So what we know is how much current can I hold those contacts closed as I ramp that fault current up, and I want to make a clean break. I don't want chatter. If you start getting chatter inside of a circuit breaker, and some manufacturers will permit that, so you got to be careful. But if you get chatter inside that breaker, you can put dimples on your contacts, and that is, what's that called? Ungood. Right, so here's your molded case circuit breakers. Now look, I can go from a 15 amp molded case miniature breaker, and we make 10 amp breakers too, all the ways up to a 2500 amp R-frame breaker. That's a big boy. All right, that's a big circuit breaker that it's pretty heavy. 2500 amps is nothing to shake a stick at. So those and you'll notice, look at the K frame goes from 70 to 400. The L frame goes from 70 to 600. So I can buy a 70 amp K frame and a 70 amp L frame and a 70 amp F frame and a 70 amp E frame, always down to a 70 amp miniature. Why would I buy a 70 amp K frame? Why? Because I want to keep those contacts closed longer for whatever reason. I might have a motor starting. I might have selective coordination issues. I don't know. I don't care. You need that. You may need that breaker to add a delay so that whatever it is that's operating downstream operates without a problem. All right. So that's the lineup, all the way up to 100,000 amp interrupting ratings. Again, those are industrial, residential, commercial. You'll see those just about anywhere. Fixed mounted, you'll have plug on. Most of the miniatures come in both plug on and bolt on. And then the rest of these are pretty much bolted into a panel board. This is the new lineup from Eaton. We have our new power defense breakers out. So go out and check out the website. Go to eaton.com. Take a look at at the whole circuit breaker lineup. That's all changed, and I'm going to talk about some of the unique features that will help from an electrical safety perspective, selective coordination perspective, and more as we move through this presentation. I might even ask somebody from our experience center to make a little debut, so stay tuned for that. Typically, your insulated case circuit breakers. Now, this is that in-between device that we put in there to give us that buffer zone between going from molded case all the ways up to power breakers. Typically you're going to go from 800 to 6,000 amps, up to 150,000 interrupting, and you have these in some sort of enclosures, switchboards and switchgear. This is another important piece of the pie. You have to understand where these breakers, I always call it wrapping steel around the breaker. You got to remember, I just don't take a circuit breaker and slap it on a wall, right? I have to put this breaker in an enclosure, and in all manufacturers will tell you what breakers can go into which pieces of equipment, which you got to think about in the design phase. If you make, oh, somebody's talking. Check your mute yourself there, whoever that is. Daryl, I got you, buddy. All right. So, gotcha. No, I can't mute you. Daryl, mute. Can't mute you. You're going to have to mute yourself. You have to mute yourself, Terrell, please. Terrell, please. For some reason, it's not letting me mute you. Terrell, you're killing me, buddy. You're killing me. Hold on, everybody. Participant, mute all. There. All right. Sorry for that little interruption there. Okay, so let me just go open up my chat sessions as well. And I'm going to open up my participants so I can see when Terrell decides to unmute. All right, so these devices are going to have to be in an enclosure. If you make a change in your design, for example, you decide you missed selective coordination and you have to increase the size of the circuit breaker. When you do that, you may not be able to put that same breaker in the panel that you have either out there already or what you were planning to put it in. So, and we'll talk a little bit about that moving forward. So these devices definitely have to be put in steel and in panel boards, in switchboards, in switchgear. Some of those enclosures give you a lot of flexibility. Some will have only specific devices that can be put inside. And then these I call the Swiss watch of the circuit breaker family. These are your power circuit breakers. We can take them apart. We can refurbish. We can recondition these. We can add a lot of different features. They look complicated. They look scary. I mean, look at those stabs on the back. I mean, it looks like something out of Einstein's day, right? So in any case, we get up to 200,000 amp interrupting ratings, up to 6,000 amp frame. And these are in your large switchgear and switchboards. These are your big devices. They'll rack out. They'll have equipment to take them out, just like the insulated case. So these are your big boys. And I don't have the medium voltage. I'm not covering medium voltage in this one here. So these are all of your low voltage power circuit breakers. And really now it's 1,000 amps and below because we changed a lot of the standards. We moved 600 volts, 1,000 volts and below. We moved 600 volts up to 1,000 volts. Recently in the National Electrical Code, which drove standard changes as well. Now, these supplementary protectors, Mr. Cernko used to tell me that he calls these devices, you use these when you don't need them. That's what he used to say. Supplementary protectors, whether it be a fuse or a circuit breaker, these were what these aren't branch circuit rated devices. These have to have an overcurrent device upstream providing short circuit and protection for that equipment. You'll see these in industrial control panels. They look like a circuit breaker. You can't use them like a circuit breaker. They're covered by UL 1077, not UL 489. And in 240.10 is the section that you'll reference for where it tells you the requirements around supplementary overcurrent protective devices. So, that's in 240.10. Remember, it does resemble a standard thermomagnetic breaker. A lot of these are DIN rail mounted. I do have one around here. It looks like that, but it's not a thermomagnetic circuit breaker. It's actually it's not a 1077 device. It is a UL 489 device. Not sure what I did with it. I got breakers sitting all around me here, but in any case, I'm moving my moving everything around. But in any case, these are not branch rated, so you got to be careful on how you use them. So let's talk about the different types of ratings. Let's talk the standard Ampere ratings. So 240.6 covers standard Ampere ratings. That's the name of the section in the code, and it handles fuses and fixed trip circuit breakers, adjustable trip circuit breakers, and then restricted access adjustable trip breakers. So there's three things that I want to cover. Bill Winston to everyone, lost the audio. I'm just going to look at this before we get in there. Everybody can hear me, right? I believe that I'm still speaking clearly. Look at my symbol. Yep, I can hear me. All right. Okay, so audio is great. Thank you very much, Mr. Kraushaw. Okay, so fuses. Let's walk our way through this one. First, fuses and fixed trip breakers. Again, now they have standard Ampere ratings for fuses and circuit breakers, and there's a table in the National Electrical Code, which we, in this 2020 version, or actually the 2017 version, they made it a table. It used to be in Word, so it was kind of confusing. But they gave us the standard Ampere ratings for each of these. Now, here's how they use this. Whenever you see in the National Electrical Code that you can use, like say it's an overcurrent protective device. I'm sorry, say it's a conductor, and they'll say that you can use the next standard overcurrent protective device size up from whatever that amp rating is. So if it's say it's 375, I can use a 400 amp instead of a 350. If it's a 102 amps of rated for a conductor, I can use a 110 amp breaker, not have to go to the 100 amp breaker. So there are those restrictions, but you go by this table. You don't go by whether or not I might have a 106 amp fuse. You don't go to that 106 amp because it's not on this table. You got to go to the 110 amp. Now I've been I have some there may be some issues around that where you might want to use something a little bit smaller, and I think technically you can, but then I don't know. Then the code specifically tells you to use the next higher size. So in any case, we'll leave that for a later discussion. But this table tells you the standard Ampere ratings for fuses and inverse time circuit breakers. So and then there's the fuses 1, 3, 6, 10. I'll mention I got this out of, this is not in the code. This is actually out of our Busman, our Eaton Busman division has this SPD booklet, which is a free download off the web. I'll put it in the link for this. It has a lot of really good information on selecting protective devices. So if you're interested in motor protection or whatever it is, Pancake, please mute yourself. Whatever it is that you need, this is a really good resource for you from understanding how to select overcurrent protected devices. It's a fuse-based product, but remember, if I say that I can use a 60 amp fuse, I can more than likely use a 60 amp breaker as well. So it does give you the fundamentals, a lot of good code references in there. We're in the process of updating it as we speak. And that one was dedicated to George Oakley. We dedicated that one to George Oakley. Good man. All right, why the 601 amp fuse? This is a breaker thing. Why do I have this in there? Well, I think I just copied some slides from 240.6. All right, so 601 amp fuse, Class L fuse for motor protection. It all has to do with the holder that I can put it in, so that I don't have to go to a next size up fuse holder. That's basically why I did that. This is a breaker presentation. You got to come. I'm scheduled Fuseology for next week, so I haven't advertised that yet, but I'll have Fuseology in there as well. Okay. Adjustable trip circuit breakers. The rating of adjustable trip circuit breakers have external means for adjusting the current setting. Not meeting the requirements of 240.6c shall be the maximum setting possible. So what this really gets into is if I'm not going to lock that faceplate of that breaker, then my conductor size, if I have a 600 amp breaker and I can adjust it down, my conductor, I have to have 600 amps worth of conductor, or I can't have anything less than 600 amps worth of conductor, because I need to protect it at its ampacity. And if I'm not locking the front of that this faceplate, then I have to make sure that I the ampacity of that conductor is not smaller than the rating of that breaker. Now, restricted access adjustable strip breakers, and that basically tells us that if I have a circuit breaker that has restricted access to the adjustability means, then I can lower. Say I have a 600 amp breaker and I have 300 amps worth of conductor. I can lower the long time pickup down to 300, put a lock on it, and seal it, and then I can sit down and say that that's illegal, and that's where I get 240.6c helps me be able to do that. Now, what we did, we made some changes in the 2020 cycle. What it used to say was you had to have a lock on it, but then there's a realization that there's circuit breakers that have electronic trip units that don't have a means to lock it, but we do have a password. So they gave us options now in 240.6 where we removed located behind one of the following, and we said located behind removable and sealable covers. So that's one option. Located behind bolted equipment enclosure doors. That's another. Located behind locked doors, accessible only to qualified persons, or and this is the one that we really added, password protected with password accessible only to qualified personnel. And you know, the electronic trip units that we have today, these types of devices are password protected. The one you see on the right, that Digitrip 520 there are dials on the face of that. You would have to meet one of the other criteria because I can't password protect that. It's adjustable at its faceplate, so that would have to have a cover or be behind a locked door or one of those options in that section. And but the one on the left there is password protected, and I could, as long as that password is only available to qualified individuals, then I'm good to go. So, and that's how you basically change the settings on these devices. You're rotating those dials. I'll never forget. I walked into a facility one time, and they basically had a case where they were taking equipment down, and the gentleman I was working with, it was a chemical type of installation. It wasn't a petrochem or anything like that. I think they did like paints or whatever it was. And the gentleman I was working with, I said, "Boy, you got a lot of work going on. What's going on?" He says, "We have to change all this equipment out." He said, "Because it wasn't working." He says, "We had a cascading event. We had the main go, and this stuff was supposed to trip, and it didn't trip. Things that weren't supposed to trip did trip. Things that were supposed to trip didn't trip." He says, "So we're changing some things out, and we're upgrading at the same time." And I was like, "Well, who did your coordination study?" And he looked at me and he says, "What's that?" And I said, "Well, David," I said, we had a device there, and I showed him this faceplate. And I says, "Who's decided what set points to put in there?" He goes, "Oh, no, Tom. We take factory defaults on all of our circuit breakers." And I had to give him an education that when we ship these, they're all set at minimum. So what you're supposed to do is have a short circuit study and a selective coordination study. And then the coordination study, the engineer tells you what these set points need to be, and those need to be programmed. Now, nobody really looks at those. Most inspectors, and I see David Platts on, I believe he probably does. I know a few inspectors that do check the long time pickup of those devices and make sure that those are set to protect the conductor. But the rest of those, long time delay, short time delay, instantaneous, that doesn't have a code reference at all. It's the long time pickup's the important one. All of those other settings have to do with selective coordination. So, but you got to remember that you have to change those, make the right set those when you install those. All right, so now we're going to talk about voltage rating. So we talked about the ampere rating. Remember, the amp rating of that breaker is really determined by the conductor that you're trying to protect or the equipment that you're trying to protect. That's what's going to tell you what the what value you need to get into. Now we're going to talk about voltage. So voltage is another very important aspect of circuit breakers and applying circuit breakers. So you're going to hear about two different voltages as we go through this journey: rated voltage and system voltages. I could have a circuit breaker rated for 600 volts, but applied on a system of 480 volts. So those are two basically different things. Remember, as long as my system voltage doesn't exceed my rated voltage, I'm okay. I can have a 600 volt breaker applied on a 208 volt system, but I can't take a 280 volt rated breaker and apply it on a 600 volt system. So NFPA 70 defines voltage in terms of voltage of a circuit, stating that the voltage of a circuit is the greatest RMS effective difference of potential between any two conductors of the circuit concerned. Now, that's an important thing to remember, and the reason is because I'm going to be comparing voltages, and when I start putting handles on handle ties on breakers and things of that nature, I have to make sure that they are still being applied correctly based upon the maximum potential between any two conductors of the circuit concerned. So we're going to get into a little bit of that as we move down the road. And voltage is important because that's the driving force. If I think about water and plumbing, the more force I have behind water is what drives that water. That's your voltage potential. Typical sources of EMF are your batteries, your generators, and things of that nature. That's your electromotive forces. So again, it's the energy transferred per coulomb when one or other of energy is converted into electrical energy. So V is equal to work over energy. So electromagnetic force. So if I take a look at a circuit like this, I can push current through this circuit. I can push 1.6 ohms. I can push 15 amps at 600 volts, or I can push 15 amps at 24 volts. It all depends upon the resistance. If I have more voltage, I need to have more resistance in the picture to limit my current to 15 amps. If I have less voltage, I need less resistance to make sure that I can still push 15 amps through the circuit. And this is basically how we test a lot of our circuit breakers. We'll test them at lower voltages, get the same amps, because the amps is what makes a circuit breaker trip. So I can establish my trip curves based upon the amps and one keep a low voltage, but just drive that amps. And this is important because the trip curve does not change based upon the voltage. If you're just looking at a TCC curve and you can say, well, this is a time current characteristic curve at what voltage? Well, it's whatever voltage that you apply it. It's how much current. It's depending upon how much current that you are pushing through the system. Where voltage comes into play is when I have if I want to plot two curves on the same time current characteristic curve in a selective coordination perspective. If this is all foreign to you, watch my my selective coordination presentation. But when I start plotting two breakers curves and there are different voltages, I'll have to shift some things around. But I'll test a lot of our breakers at a low voltage because it's safer. Safety is key. Now, really, in a power distribution system, your transformers establish the voltage. If I look back up there at my utility, I got Tim Krauscher pushing stuff back to me. I got 4160 on the line side, 480 on the secondary. I know it's a delta Y grounded system. That tells me a lot. That tells me what my line-to-line voltages are, my line to neutral and line to ground voltages, just by knowing that the secondary of that transformer is 480 and it's a Y-grounded system. If it was a delta-delta and it was 480, that still tells me a lot. I know what all of my voltage potentials are. So the transformer is a critical piece to help us understand what the voltages are. Most common configurations are found 208 volts. This is your Y-grounded system. Again, you have voltages difference between the phases. And if you think about like a circuit breaker, if I have a circuit breaker, if I put a circuit breaker in here that is that has, say, a rating of 208 to 120, or 120/208, or 120/240 volt breaker, a slash rated breaker, that slash rating tells me that I can interrupt the currents at both the 120 volt level, and I can interrupt the line-to-line currents, the short circuit, and I can perform when I have 208 volts applied across that circuit breaker. So those are tests that are done, pole individual and line to line that are done. If I have just a circuit breaker that's rated 120 volts, I only test it at 120 volts. I don't test it to interrupt a current that's being pushed by 208 volts, right? So the voltage potential does make a difference in the interrupting capability of that circuit breaker. You'll have different interrupting capabilities based upon the voltages, and we'll talk about that when we get into interrupting. But I have to make sure that I apply my circuit breaker correctly. And this one here, these types of systems, they're 480 volts, straight 480 volts. I can't, I have to make sure that I have a straight rated circuit breaker in there that's rated to handle 480 volts. And most of our breakers that you would see in this application are 600 volts anyway, so everything's covacevic. And there's your corner grounded delta. These became very popular back in the day when we were moving from ungrounded to grounded systems, because of that newfangled thing that we learned about with, we are having all kinds of issues back in the day with over voltages due to ungrounded systems, and they decided to ground them because it's like the boat floating in the water. If you don't have the boat and the anchor down, you'll float wherever you want to go from a voltage perspective, wherever the water waves take you. But when you have it grounded, when you put that anchor down, now you are controlling your voltage spikes in your system during abnormal events in the power distribution system. And then you could take a normally delta system, corner ground that system, and now you have an effectively grounded system. And then this is your high leg deltas, your center tap delta. You'll see this. I think you'll see a lot of these types of configurations. There's other configurations too. The utility guys do some funky stuff and crazy things. When they try to deliver power down to a residence or whatnot, you'll have your open deltas and things of that nature. There's different ways for them to configure things. You're going to want to look at the circuit breaker and make sure that the voltage rating, so you'll notice this one says 600 volts AC, 250 volts DC. That tells me I can use it on an AC system and a DC system. You'll notice that I can use it on a 600 volt AC, but not a 600 volt DC system. I'm doing it at a reduced voltage, and on this same circuit breaker, more often than not, it'll tell you how to wire this in the picture. I hope I have a DC breaker picture in here. I'm not sure if I put that in there or not. Here is a slash rated breaker, 480/277. Hacker rated, interrupting ratings. It has all that information right there on the face, like David Williams loves. I know David Williams would love all the miniature breakers to have those names that information on the faceplate, visible through the dead front. And I'll explain these labels as well. I've got a good reference for you from UL. There is a there's a device, and that one looks like a supplemental device, doesn't it? Remember the picture I had earlier? But look at on my pen, on this, I got to maximize this. Look at this. Look what it says. Whoops. I'm sorry about that. Gotta go back. Ignore the man behind the screen. Look at what it says right here. You see that number? 489. It's hard to read probably on your screen. 489. You know what that means? UL 489 listed. So although it looks like a supplemental protective device, it is really and in fact a listed UL 489 device. So you're looking for the listing marks, and that's 480/277. And every, circuit breakers and fuses aren't the only devices that'll have voltage ratings. All of this different equipment will have voltage ratings. There's 460, 3-phase, 60 hertz, 70 hertz too. I don't know. 60 hertz. This here tells you, where's it at? Voltage 208, 240, 480 on the input. DC output per the circuit is 24 volts, maximum amp. So, all of the equipment that we apply in a power distribution system is going to have a voltage rating because we've got to make sure that we are applying the equipment correctly. And the voltage rating of the equipment may limit your use of that equipment. For example, if you have a slash rated device and then in one plant, that's say a grounded system, but you have an open delta or a corner grounded delta system in another plant, and you want to take that same piece of equipment that's slash rated and use it over there, you can't because of the voltage ratings, and you might be exceeding the voltage ratings. You can't exceed the line to line, can't exceed the higher number. The line to neutral can't exceed the lower number. So in a corner grounded delta system, you could exceed the voltage ratings of some of these interrupting devices, some of these overcurrent devices or equipment. Just not just an overcurrent device. It could be an industrial control panel. All right. Voltage marking. So in 24083, it tells us that we need to mark the voltage, and it says it has to be marked with a voltage rating not less than the nominal system voltage. And we already said, read what the nominal system voltage is. The voltage between any two conductors, that's indicative of their capability to interrupt fault currents going 100 miles an hour. So in 110.4, throughout the code, the voltage considered shall be that of which the circuit operates. The voltage rating of electrical equipment shall not be less than the nominal voltage of a circuit to which it's connected. So this is my point earlier. You're going to see a couple terms used. You're going to see a system voltage. You're going to see the voltage in the system at which it's applied. And then you're going to see the rating of the voltage rating of the equipment. One has to be greater than the other, just like we talk about interrupting ratings and etc. Now 280.2, this is now reason I put 280.2 in there. Transient. So I'll get to comments. I'm not going to look at the chats yet. I'm going to look at that in a little bit. So 280.2, the reason I put surge arresters cannot be installed where the rating of the surge arrestor is less than the maximum continuous phase to ground frequency voltage. That's over 1,000 volts. It just brought to my mind that to remind everybody that we do have surge protective devices. Like in your 285, 285.3, where you have an SPD that could be built into the circuit breaker. You could have we have circuit breakers that do a dual function in that regard, where we have say a 60 amp or a 50 amp thermomagnetic 2-pole breaker that also provides surge protection. So it does two things. The hardest part on most of these is to, do you have an extra slot in your equipment, in your panel board to be able to put another breaker to feed a separate surge device? Well, we built in, and we offer surge built into the standard breaker, so you can serve a 50 amp load and provide surge protection at the same time. That can be a savings to not have to put another panel in. Where the rating of the SPD is less than, so we got to consider voltage in all equipment. So straight rated versus slash rated, you have 2-pole devices that are can be applied on 3-phase corner grounded delta systems. We already talked about that. That you have to be careful of the bigger number and the smaller number, and it's just basically how we test it. We test to make sure that we can interrupt faults line to line, and we interrupt the line to ground or line to neutrals. So we know the capabilities of those devices. You've got to make sure that you're following the rules in 24085. I know there's a lot of words on here, but basically what this is telling you is that your slash rated breakers can be applied on solidly grounded systems where you don't exceed, the line to line doesn't exceed the big number, the line to neutral doesn't exceed the lower number. And your corner, if you're taking a multi-case circuit breaker and you're going to put that on a say a corner grounded delta system, you have to also consider the individual pole interrupting capability. Again, it's just a very important reference for you. Every now and then I look over a chat and I got to not do that. In 240.15b3, it tells us that, again, your voltage to ground cannot exceed in 120 volts in that 240/120 application. So when you have these slash rated breakers. So you're looking at the line to line can't be greater than the big number. The line to neutral can't be greater than the smaller number. And this is why, like AFCIs and GFCIs, this is another reason. If you have a circuit breaker that's straight rated 120, you cannot put a handle tie on it because then you exceed the line-to-line voltage now, because now you've got a two-pole breaker where you've put a handle tie. And remember, the rating can't be less than the system voltage, which is measured from conductor to conductor. And if you put a handle tie, you have a 120 volt, now you have a 240 volt, conductor to conductor is 240 volts. You've misapplied that breaker. This is B4, 3-wire direct current, same type of deal, does not exceed 125 volts, voltage to ground. So you're looking at the voltage. You got to make sure you compare the right voltages for a lot of different reasons. And anytime you're going to, so if you have a standard thermal mag breaker, most of those standard thermomagnetic breakers will have a slash rating. You'll notice on this one here, this breaker right here, do you see the label right there? It says classified product. That doesn't mean it's top secret. That doesn't mean that you're going to have to race your hard drives now that you've seen this product. That just means that you can put that product into other manufacturers' panel boards as long as you follow the instructions and only put it in the panel boards that are listed there. And again, 240.15b1 talks about multi-wire branch circuits. Individual single pole breakers with identified handle ties shall be permitted as the protection for each. And that is not an identified handle tie. I took that picture at a local church near me. They asked me to take a look at some things and help them figure out what they needed to do. And I said, you need to fix this one right away. You can't just take copper and stick it in there. That's ungood. Okay, so this talks about, if you take an industrial control panel, and that industrial control panel not only missed that branch, but it was way off of probably the plant property. But in any case, you've got to be careful that if you're using slash rated devices and you go from a Y grounded system and you have another plant that's corner grounded delta, this is why planning up front, when you order equipment, if you order something that's straight voltage rated, you can use this in any one of your plants and facilities. If you don't do that, then you could possibly have a problem if you're in that world of moving equipment from one place to another. Conductors of different systems. I'm not sure why I put this in there. Again, this is just voltage consideration. So what I'm saying is, what I'm trying to help you understand is it's not just circuit breakers. There's every piece of component that you have, wire, control panels, breakers, fuses, no matter what it is, they're all going to have voltage ratings and you can't misapply that. So, and this is just up in Article 300 talking about general requirements around those conductors. Again, even equipment, all equipment is going to have a voltage rating. You can't, it'll have to be marked with the maximum voltage ratings. Spacing in cabinets. I talk a little bit about spacing in here just to help you understand. Again, live parts, there has to be certain spacing between the walls and the gutters and things of that nature. So a lot of this is a part of the UL listing standard when we create things and create products and solutions. Dielectric voltage withstand test. So this is, when you look at UL 489 and other standards, we do what we call dielectric voltage withstand test. That means as you raise the voltage for those transient events, I saw somebody up there on TubeLand asked a question about transient voltages and things like that. We have testing, and we will do dielectric tests, and we'll put specifically, we have requirements where we have you call it spacings in there in between those breakers to give us enough space so that we don't have tracking and tracing from, so say, lug to terminal, and they in the standards they go into specifics on what those spacings need to be. This is a lot of, you don't have to. I'm not putting the words up there to help you read that. I'm just putting the words up there to just to speak to it. But there are spacing requirements, and there are in the standards they tell you through air and over the surface, between terminals of opposite polarity, between terminals and any ground. So these are all part of the UL testing. So if you look at the terminals, they'll tell you from a manufacturer's perspective, I'm maintaining certain distances, and I'm doing certain things in testing to make sure I don't have tracking over these conductors and across terminals, right? So, and you may see barriers built in. You may see some fins and go, why did they put this big piece of plastic here? And it's because I need to pass some of these tests when we test the UL49 device. So you can't just say, I'm going to break this off because it's in the way, right? That would be ungood. When you see these protectors and you'll see terminals like this, and you'll have these little chutes, they look like up here, where you go, wow, why do I have to install that on this application? And why do they have these little tubes sticking up where I'm putting my screwdriver down in there to tighten lugs and whatnot? Well, that's because I need to maintain tracking and prevent tracking of voltage for these higher voltages. And you may see a line side adapter like this on the top of starters and things like that. That's all there to make sure that that I don't have problems when I have these transient voltages. I have creepage and clearances that I have to maintain on our equipment. You don't want to be modifying that in the field. That would be ungood. Word of the day. Clearance and creepages. So we have to keep measurements. So you'll see fins in between terminals. You'll say, why the heck did they put this fin? It's keeping me, and I keep getting my little conductor stuck in this one fin, and I wish I would just take it away. Well, you can't do that. The reason these types of fins are there is because I need to maintain distances between my terminals, either over like that or along the surface. I may have to have so many inches or millimeters or whatever meter eaters. I gotta have my certain distances. That's creepage and clearance, right? And there's information on terminal blocks, and if you're familiar with picking terminal blocks and all of these little fins that you might see on a terminal block, it's the same basic principle on molded case circuit breakers whenever we're doing these tests. So that's the voltage discussion, and that's all I have to say about that. I'm going to take a look at the chat now. I see a lot of stuff going on in chat. I'm going to look up on my tubers. I don't understand the handle tie comment, since nearly all circuit breaker have trip-free handles, so simultaneous trips are not forced on the other handle tie. Okay, Jim, that's true, but the handle tie is needed not for tripping purposes. If I'm sharing a neutral and I take a shared neutral down to a box, the code requires me to put a handle tie on there so that whenever I turn that breaker off, I turn both breakers off, because I have two hots and a neutral going to one box. I have to make sure that I don't just turn off one pole and leave something energized in there. The handle tie is not there to make them both trip. The handle tie is there only to make sure that you are turning both of those circuits off. Do breakers have a maximum transient voltage withstand capabilities? We have the testing for the harshest conditions that you'll see which I covered, why we have the creepages and clearances. I've never seen a transient voltage rating personally on a breaker. I may be wrong on that one, but I don't think so. Luis, but can you watch it later, take notes? Yes, you can. This is going to be on YouTube. I have so many end users and contractor customers that want us switchgear manufacturers to tell them how to set their breakers. Yes. And here's the thing. You know what I would say to that? Do it. We can do it. We have most equipment manufacturers have a services division, or you take the order and you hire somebody to do that. I would rather say, I'll do it. One of my things one thing about me is ownership. And I learned that when I first started with Eaton. I was on a help desk. I went from a design engineering firm, Gilbert Commonwealth, where I was working in a nuclear plant. I was designing, I was doing coordination studies, short circuit studies. I laid out the security system for the Crystal River Unit 3 and whatnot. And I went to a help desk, and I was thinking, oh man, I'm going to a help desk. I loved that job because when people would ask me questions, I took ownership of that, and you help them out. I would rather take a customer who says, will you set these for me? I would say, yes. And here's how much it's going to cost you. And we'll get a contract put together, because if you don't, 9 times out of 10, it doesn't get set, and 9 times out of 10, they're willing to, they understand if they're asking you those questions, they understand that it needs to get done. So you need to do the study, but then you need somebody actually out there to go out there and actually program the settings. Pausing to take notes. I'm just looking through the comments here. What are the safety precautions in circuit breakers? We're going to talk a little bit about that. Settings, changing settings and whatnot. A lot of that's done, hopefully, without it being energized. What could happen if you change some of those settings is you could cause a trip, and that might be ungood depending upon what's going on. And not just because of the breakers, because whatever you're serving. There are a lot of reasons why you should probably plan. If you haven't set these breakers, you'll probably want to take that down, do your maintenance things anyway, program those set points and get that back up and running, because you never know what the loads are downstream and all the different things. You don't know what the maintenance history of that circuit breaker is. All right, so that's all on that one. Let's take a look at chat on WebEx. Scritty has 2-pole circuit breakers rated 122/40 and others rated 240. It's just the systems that you are going to apply those devices in. That's all. And everybody will do it differently. So don't take one manufacturer and think the other manufacturer is doing the same thing. When setting the trip for an adjustable trip breaker that complies with 246C, and I still make the setting match the next standard size, or must I match the setting to the exact conductor ampacity? Does the rating plug count? So again, look at 240.4B2, and you Don. Oh, that was from, I don't know who that was from. When setting the trip for an adjustable trip breaker that complies with 240.6C, 240.6C. I gotta get my book. I believe that's the one with the restricted access. Yep, restricted access. And let's read that. A circuit breaker that has restricted access to the adjustment means that permitted to have an ampere rating that is equal to the adjusted current setting. Restricted access shall be achieved. I think I know where you're going, Dawn. I think that's you, Dawn. You still make the setting match the next standard size, or must I match the setting to the exact conductor ampacity? The code says you can go to the next size up. So you can go to the next size up. You don't have to match the ampacity. That would be my answer. I don't know if that's right or wrong or different. That would be my educated guess based upon what I know about the NEC. The NEC says you can use the next size up, and so that means you can adjust it up to that next size. My suggestion would be to match the conductor ampacity, but I don't see there's anything in the code that addresses that scenario that you just raised about adjusting it exactly to it or adjusting it to the next size higher. All right. Okay, so let's boogie back to our regularly scheduled program. Interrupting rating. An interrupting rating is the highest current an overcurrent device is rated to safely interrupt. That is the stopping of the flow of current during a short circuit. Or it could be, it just dawned on me. I was talking to somebody about interrupting rating, and I was corrected. And this is the fun part: is when you think you know something. And I've been doing this for a long time, and they said, "Well, Tom, no, you got to look at the interrupting. Take a look at the definition of interrupting rating." The interrupting rating says the highest current at rated voltage that a device is identified to interrupt under standard test conditions. And there is an informational note. Equipment intended to interrupt current at other than fault levels may have its interrupting rating implied in other ratings, such as horsepower or locked rotor current. So An interrupting rating is not always just fault current. It's whatever the highest current that that device can stop from flowing. Now let's take a look at what happens when you misapply a product. Whoops. These are fuses and circuit breakers misapplied. An interrupting rating of a class, this is a 10,000 amp interrupting rating class H fuse and a 14,000 circuit breaker. This is what happens when you make a mistake. You have to apply the devices within their interrupting
This is a
rating.
serious misapplication.
It sure is. If you don't, when they try to stop the flow of current, they can achieve an unintended rapid disassembly in the field. So 24083 tells us that every circuit breaker has to be marked with its interrupting rating, except for those that have an interrupting rating of 5,000 amps. So this is that question that we had on the quiz. If it's not marked, it's 5K. If that's basically what you assume on an interrupting, that's your lowest that you could possibly go. Although we only make 10K. If it's not marked, it is 5,000 amp interrupting rating. So the key feature again is to stop the flow of current. Overcurrent devices have to have adequate normal current ratings, and interrupting rating is not the instantaneous pickup on a circuit breaker. Another very important thing to remember. Overcurrent devices in Article 100 it tells you what the definition is, and then there's the requirement in 110.9 that tells you you can't exceed the interrupting rating when you apply it in the field. They have to be greater than or equal to the maximum available fault current. And these are the minimum interrupting ratings of any overcurrent devices. Fuses are 10,000, and 24083C tells us the minimum is a 5,000. And again, it doesn't apply to supplemental protective devices. We don't publish that. And you'll see that the faceplate of these devices have the interrupting ratings, and it'll change based on the voltage. And you can look at this one. At 240 volts, it can interrupt 65,000 amps. At 480 volts, only 35,000 amps. So, and at 600 volts, only 18,000 amps. Make sure you put it, if you understand the voltage you're applying it at, because that will determine what the interrupting rating is of that circuit breaker. And there's your rating on this E-frame breaker, 240. At 240 volts, 200,000 amp interrupting. Very cool. But if you're applying it at 600, you're only at 35. Don't make that mistake in the field. Short circuit current. This discussion of, we calculate the symmetrical. We know that during a short circuit, we're going to have asymmetrical flowing. That peak current is going to be much bigger than what the symmetrical is. But what we do as a circuit breaker manufacturers, we test our breakers for this worst case scenario, but we label it based upon an RMS value. And then, this is what current limitation does for you, whether it be fuses or circuit breakers. You're going to be clearing this device when you're in the current limiting region. You're clearing it less than a half cycle. This right there is a half. So right there is a half cycle. Right there is one complete cycle, 2 complete cycles, 3 cycles, 4 cycles, 5 cycles. That's basically what you're seeing there, and you'll see a natural decay. But this first half cycle. That's the worst one to hardest one to interrupt. And that offset's going to be dependent upon the X to R ratio, right? And we test breakers at a 6.6 X to R ratio. That establishes the power factor of that equipment. This is a purely resistive circuit. Your current and your voltage are in sync with each other. They both cross zero and they both peak at the same time. A highly inductive circuit, the voltage peaks when the current is zero, and the current peaks just about when the voltage is pretty close to zero. Capacitive circuit, Voltage peaks when the current is 0. The current's peaking when the voltage is around 0. That could be very difficult to interrupt. Right? X to R ratio of a circuit with an 80% power factor. We use our standard, or what we learned in geometry. You know, we have R squared plus X squared equals C squared. Square root of all of that, sum of, you just use your standard equations to calculate angles and to know what your hypotenuse. There's your hypotenuse. There's your reactance and your resistance. Your real components are across the bottom. Your reactive components up the side. This is what we call the power triangle, right? And I had a class on this as well last week when we were in our fault current discussion. So when our power factors change, the worst case is right down here at 6.5 and a 15% power factor, right? So if power factor, if the angle is getting greater, reactance is getting larger, and the worst case scenario is when that angle is at 81.37. So what you'll want to do when we tell you what an interrupting rating breaker is, we know that the X to R ratio is around 6.6 right here. If your X to R ratio is greater than 6.6, which is pretty rare in a power distribution system, you're going to have to derate the overcurrent protective device. And you'll see that on your short circuit studies. And these are just a few slides showing you what's happening at 80% power factor. Watch the peaks. One's the current, one's the voltage. Solid is your voltage, dotted lines are your currents. Look what's happening at 70% power factor, you're getting some lagging there. At 60% power factor, your waveforms are separating. And when you'll get to a point when this peak voltage is when that sine wave and current is 0, but your current is peaking just about when your voltage is 0. We love zero crossings on current, not voltage. That's why it gets harder and harder, and that's why you may have to derate interrupting if your X to R ratios go out of whack. And if you're close to because if your X is really high, that means your source is really high in X, you're probably really close to a transformer. Right, so 6.6 or less is what you're looking for, and that's at a power factor of 15%. If you're greater than 6.6 on an X to R ratio when you look at your short circuit study, you're going to need to take another closer look at the interrupting ratings of your breakers. Doesn't mean you may not have to change them, but. And there's just a picture of limiters on a breaker. You say, how do we get 200,000 amps? Well, we put these limiters in series with that breaker, and that limiter will protect the circuit breaker by, again, taking that waveform. Instead of seeing this, you're only going to see this. Instead of seeing that huge waveform, you're just going to see a little blip. You know why? Because these little guys did their job. Now, we're going to talk a little bit about other ratings. Circuit breakers have different types of ratings. HID ratings, high intensity discharge. This basically, people ask me, what are we doing with HID differently? If you look at the standards, the UL standards, basically, if you think about what's happening with HID lighting, they're typically using the circuit breaker to switch them off and on. You don't have a separate little light switch that you're using. So you have to address some of the higher inrush currents from those lightings and the fact that these are going to be switched more often and more frequently. So they have to undergo additional endurance evaluations to demonstrate their ability to perform the switching duty. So here's what we do on a circuit breaker 58 in 489 that's rated 50 amps max, 480 volts or less. We take to switch high intensity discharge lighting loads shall, in addition to other requirements in this standard, be subjected to the endurance test, a 7.1.5, and the temperature test. Okay, and if you looked at those sections, you're going to see subject to the temperature test in 7.1.4 after operations of endurance. The load shall have a power factor, so we modify that. We identify the power factor of the load, and again, that power factor of the load. If you understand that waveform that I was showing you in the X to R ratio, you're understanding now the difference between the voltage and current that we're trying to stop the flow of current on. And then you have the cycles of operation down here that we have to do, and that's all in the high intensity discharge. A circuit breaker intended to switch HID lighting loads on a regular basis and complying with the performance may be marked HID. If it's not marked HID, then it shouldn't be used on an HID type of load. Now then there's switch duty. These are suitable for switching fluorescent lighting loads. Okay, this is right. This is going to be out of the standard. I have some people that'll use SWD on HID lights. This SWD was they are suitable for switching fluorescent lighting loads on a regular basis, and that's right out of 240.83D. They're evaluated for high endurance testing, and they will the same type that we use for a light switch, because these breakers are usually, you figure out a plant uses them and they're switching all of these fluorescent lights on and off. But if you're doing HID, don't use an SWD breaker on it. Buy the right breaker for the load. So circuit breaker intended to switch fluorescent lighting loads on a regular basis. They have to comply with the construction requirements, everything in 6.1. So that's your standard stuff. And to switch, again, 15 or 20 amp or less, intended to switch fluorescent lighting, you probably wouldn't have HID at 15 or 20, subject to the endurance and temperature tests. And then you have your temperature tests. Again, there's your 7.10. You have temperature tests. And where's the where's your cycles? There's your cycles. Okay. And what I'm not seeing here is the power factor for the load. We had that on the HID, but we don't have that on this one. All right. So, and if it passes those tests, you can mark it SWD. Hacker rated. I don't believe hackers anymore. It was removed from UL. There it is, 1995. You may still see those labels on it. We just keep them on there. I don't know. I think it's a sense of love for that acronym. But it's not required by the UL 1995 product standard, and it's been removed. So it's not necessary. If you have it on that breaker, it's extra icing for the cake. Switch fluorescent. So 240.83 includes requirements for circuit breakers used to switch fluorescent and HID lighting circuits. Does the NEC other codes or engineering principles require the same concern for incandescent or LED lighting circuits? And no. Now I've heard some people have had issues on LED lights, probably because of the inrush on the LED circuits, drawing for the drivers. I've heard of that, but there's nothing that like SWD or HID in the standard to handle LEDs. 240.83 just talks about breakers that are used as switches, and they can be either HID or SWD. There's nothing in there that talks about LED. Another opportunity for the breaker guys, right? There's no special rating for LED lighting loads. All right, so we're going to talk a little bit about the construction. It's important to understand the construction of circuit breakers. You have all the different parts. You've got the molded case out here. This is your handle mechanism. Here are your contacts over here. This is going to go up and down, and they are going up and down in the middle of what we call the arc extinguishers. And then you have your arc chutes, which ventilates out the back of the breaker. You have your contacts. This contact configuration is what helps us get a current limiting type device in a circuit breaker, because we leverage the fact that these magnetic fields will propel each other and push those contacts away from each other. So that's we double back or reverse loop type of design. I went to one of our engineers on breakers, and I asked him, I said, I'm trying to put a PowerPoint presentation together, teach people about breaker basics. Can you tell me what are the materials we use on the contacts? And he says, what voltage? What amperage? Which breaker? What style? They're all over the place. So we combine tungsten and silver. Tungsten gives you your porous. Silver fills the gaps, and the tungsten is what's really durable and will last. Obviously, silver's a little bit probably is softer. So we get durability, and we worry about temperature, and it's a recipe. I'm sure we pay. We have engineers who just do that for a living, worrying about the contacts. The arc extinguisher's job is to take the current and stop the flow and help extinguish the arc, cool that arc, and separate it and divide it. And you have magnetic fields to draw that arc into those plates, and all of that has to happen very quickly. And then the gases expel and go outside of the back of the breaker. Now, the thermal and magnetic, your thermal basically is two different metals. That's why they call it a bimetal. You have two different metals that expand and contract differently based on heat. So what happens is that metal bends, and then it hits a latch and causes the breaker to trip. And on the magnetic portion, we show a coil here, but in reality, it's more like what I call the clapper in most cases. We do have breakers with coils in them, but for the most part, and I'll show you a picture of it. You know, on the magnetic side, you have a lot of current going through it, and it causes a plunger. But I'm going to show you a little demonstration of a thermal magnetic circuit breaker, residential miniature type breaker. All right, so basically what's happening is we're heating a bimetal that's going to bend and turn and cause that coil to trip, just like you saw. And that's the thermal side of the picture. And then on the instantaneous side, you're causing a very high fault current to flow through, and it pulls in the circuit. I call it, I lovingly call it the clapper, and it basically will cause it to trip very fast. Now on the larger breakers, to show you that I'm not all that crazy, this is sort of a thermomagnetic trip unit that you might see on a larger. This is an 800 amp breaker, and you'll see there's 3 dials on the face of this device that controls the instantaneous pickup of that breaker. You'll see it. This is what it looks like inside of a breaker before it's closed up. That's where it sits, just below the handle. And then those are what we call that. Remember in the small breaker, we saw it trip, and but That is the portion of the circuit that that opens. I lost my pen. So that clapper is what's pulled in and stops the flow of current very fast. That's your instantaneous portion. And that's just a better shot of it right in here. So this is that's your clapper that's going to be sucked in and causes it to trip. And you'll notice the dials are down here in the front controlling this on the distances. So it's a very mechanical device. I remember the first time I came to Eaton, I was really nervous because I figured I'm going to be in the presence of a lot of smart electrical engineers, and it was like everybody I met was, yeah, I'm a mechanical engineer. Yeah, I'm a mechanical engineer. And I asked the one guy, I said, boy, there are a lot of mechanical engineers in here. And he goes, did you ever look at a breaker? He says, very mechanical device. And he was right. Very mechanical device. I see my pen. I dropped it. All right, got my pen back. Okay, so let's talk a little bit more. Provided by us now, overcurrent protected devices. Those two portions help you understand the time current characteristic curve, because the thermal portion of it impacts this portion of the curve. The magnetic portion is the instantaneous. Okay, now remember that instantaneous is there to protect the breaker. It's not there because the standard tells me to be there. That's how we comprise that time current characteristic curve. And if you don't know what the TCC curve is, you have current across the bottom and you have time up the side. So it's current versus time. And then we plot the trip curve. So for any value of current, I can go up and figure out the maximum and minimum clearing times for this circuit breaker. This is a thermomagnetic circuit breaker. This is a thermomagnetic circuit breaker that has an adjustable instantaneous, just like the one I just showed you, where you have those three dials. There's a thermomagnetic breaker that just it is what it is. It's a 600 amp thermomagnetic breaker. There's no adjustability to that. And then, okay, so that's basically how breakers have been built for years. And then all of a sudden, we came out with electronics. In 1973, the electronics breaker was put into the marketplace. You got to think about what was going on in the 70s and the size of computer rooms back then. So being able to put electronics inside of a small trip unit to operate a circuit breaker was huge. Power systems moving from the power systems were moving from ungrounded to grounded system, from 208 to 480 volts, from 600 amp to 4,000 amp services, and they realized because of the burn downs, they needed to do something to address the arc flash events that they were having at service entrance equipment. And so Westinghouse, I believe, was the first one that said in 1973 they married electronics with a standard thermomagnetic circuit breaker, and they changed the history of circuit breaker technology when that happened. When they took a brain and put it inside of these types of devices, which was the Celtronic circuit breaker back in the day, they were able to do things that circuit breakers were not able prior to do at all. They added current transformers inside those trip units. They had a little brain inside that trip unit. They had the flux transfer shunt trip. I mean, that sounds like something from Back to the Future. And that equipment, that capability, took those trip curves that we knew that were nice, big, and fat, and they streamlined them up, and they added all kinds of functionality. I've got long time pickups now. I have long time delays. I can adjust the set points and change how this trip curve looks. And you'd say, why would I do that? Well, let's say that I have a fuse downstream and it's right like this. And I'm trying to selectively coordinate. And I go, well, shoot, I'm overlapping right here. And someone says, well, wait a second, let me just make a change to the set point. Now that goes away. Well, now I selectively coordinate in that region. So I gained this capability for selective coordination reasons, and or I could say I'm taking that short time delay out of the picture altogether, and maybe that's because I wanted to Maybe that is because I've got a motor that has a start curve that looks like that. And if I don't have that, then I'll trip that circuit breaker on motor starting. So I add this intentional delay in that long time region, and boom, I can start that motor. Bam! It's in there. So 600 amp molded case circuit breaker. Now these are, I have a 600 amp molded case. I'm going to show you a 600 amp insulated. We already talked about the insulated case. There's a 600 amp insulated case. You'll notice I have a lot more functionality. I've got a higher instantaneous pickup. I have a short time delay capability. I have an adjustability here. I have adjustability here. I can move these curves back and forth. And then I can take a 600 amp power circuit breaker where I can turn off instantaneous altogether, and I can have a circuit breaker no instantaneous and 30 cycles of delay. That big boy's got to hold those contacts closed for 30 cycles. So the electronic trip unit gave us a lot of capabilities, gave us GFPE, arc fault circuit interrupters, ground fault circuit interrupters, zone selective interlocking, arc reduction technologies. I'm going to have one of our guys from the Experience Center give us a little bit more background. I'm going to have him give me a little bit of background. Come on, speak.
And the answer is complicated. Some circuit breakers don't see a lot of fault events, if any, so they tend to last a long time. Other breakers will see a really high short circuit fault, protect the system, but then need to be replaced almost immediately. Some breakers are in remote locations and no one ever turns them on or off. Other breakers get a lot of physical use as an on-off switch for a machine or a motor that can wear them down over time. There are so many factors that go into the life of the breaker. It would be nice to know exactly when a breaker needs to be replaced before an event compromises that breaker's ability to turn the power back on. Unplanned downtime for users like online tech companies, manufacturing plants, or wastewater treatment facilities could cost them anywhere from hundreds to millions of dollars and present safety issues. The good news is that Eaton is full of experts that have analyzed how different conditions affect molded case circuit breakers over time for several years. Power Defense molded case circuit breakers with PXR trip units offer a unique feature called Breaker Health. Breaker Health empowers the trip unit to monitor conditions that affect the health of the breaker, such as overload events, short circuit events, breaker operations, or how many times the breaker is turned on and off, when the last operation took place, how long the breaker has been in service, and the internal temperature of the breaker. All of these metrics are combined with a proprietary algorithm to provide a metric showing the health of the breaker. This metric is presented like the battery life on your cell phone, and it's also available as a percentage from 0% to 100%. Over time, the health will degrade depending on how the breaker is used. If it is operated excessively and sees a lot of faults, its health will decrease quickly. If the breaker operates in steady conditions, the health will not decrease as quickly. Now, instead of facing unplanned downtime, users are notified when their breaker health is low, so they have time to plan an outage safely and efficiently to replace breakers as necessary. Power Defense provides peace of mind with preventative maintenance notification to keep things running smoothly.
Cool beans. So, you got a lot of information available in these devices today, and this is critical for 70E. Think about it. I have to know the capabilities of the devices upstream, the maintenance, condition of maintenance, when I'm determining my personal protective equipment.
Some circuit breakers don't see a lot of fault events.
All right. So what about communications? Do I, I'm going to hopefully have him share a little bit of information about communications.
All of these state-of-the-art features wouldn't be very useful unless they could be accessed remotely from the breaker. Just as new technologies are emerging for us to talk remotely to our thermostats or lights in our home, Eaton has invested in better ways to talk with our Power Defense circuit breakers. All of the PXR trip units have a micro USB port that can power the trip unit even if the breaker is not installed or powered up. This port is also used to connect to a laptop and our Power Expert Protection Manager software, or PXPM. PXPM is your one-stop shop to get all kinds of information out of the breaker. You can upload and download protection settings and see the resulting time current curves. You can access historical data through a comprehensive event log. You can pull live metering data, and you can capture waveform data before and after a fault event. Everything is secure and password protected, and now it even offers a new form of testing. In the past, our legacy products used a separate test kit to test the protection routines and trip actuator on the breaker. Now, with PXPM, you can actually do a secondary injection test with just your laptop, sending a signal into the breaker CTs to simulate an actual fault, and the breaker will respond just as it would if the fault was real. After the test, PXPM even provides a clean PDF test report detailing any changes in settings, what protection settings triggered the trip, how fast the breaker reacted to the fault, and it even has room for customization to include customer and assembly information.
All right, so what you're seeing is the electronics added all of these additional capabilities. And it's important to understand that these capabilities can be leveraged for safety, for testing, and all this other good stuff. And there's a lot of things that we can do with the additional capabilities, including ground fault protection of equipment and zone selective interlocking. We talked about zone selective interlocking before, about the ability for two devices to identify, and you wire these two devices together and they can identify when a fault is either downstream of both of them, like in this case, where they both will trip based upon their set points, whatever those set points would be. If you didn't set them, you could have a cascading event. If you did set them, they may be selectively coordinated or coordinated to some fault current value. But when zone selective really takes into control is when you have a fault inside of that zone of protection and the upstream device trips very fast without an intentional delay. Now you have a zone of protection, and you have to understand what the zone of protection is, because zone selective interlocking doesn't provide protection for anything that's on the downstream side of this breaker. Because when you have a fault that's on the downstream side, this device upstream and this device downstream both go based upon their settings, whatever those settings are. And we've used this for years. We've had zone selective interlocking in equipment to protect equipment from internal faults, right? So it's important to understand what is the zone of protection. And here's the basic, the value that you get out of it. When you have a fault in this scenario, you could have, without zone selective interlocking, 43 calories per centimeter squared for a fault in that zone. But if you have zone selective interlocking and it trips around 0.08 or 0.07 seconds, you reduce that to 7 calories per centimeter squared. That changes how our guys would be dressed. It changes the amount of damage to that equipment. Zone selective interlocking is a very important value prop that we get because of the brains that we put in these devices. The arc reduction maintenance switch is another big value prop, and then we have a little video to help describe and show the value of that.
Here is how a 600 amp molded case circuit breaker set to trip via its standard instantaneous function responded to a 5000 amp arcing fault at 480 volts.
3, 2, 1, 0.
Next, let's take a look at the same test conducted on Eaton's 600 amp LG molded case circuit breaker in maintenance mode, which enables Eaton's arc flash reduction maintenance system.
3, 2, 1, 0.
Let's review the data. Current, voltage, and time are all determining factors of the
Ignore the hazard risk category because that's no longer valid in 70E, just saying.
magnitude of arc flash energy. Both circuit breakers were tested with roughly 5,000 amps of peak fault current at 480 volts. While the 600 amp breaker set to trip via its standard instantaneous function took 43.7 milliseconds to clear the fault, Eaton's maintenance mode enabled LG molded case circuit breaker took only 16.9 milliseconds to clear the fault. The resulting arc flash energy measured 0.48 calories per centimeter squared for the standard instantaneous trip versus only 0.27 calories per centimeter squared for Eaton's maintenance mode enabled breaker. The results are clear. Eaton 600 amp LG molded case circuit breaker with maintenance mode cleared the fault nearly 3 times faster than the standard instantaneous trip, resulting in a 44% reduction in arc flash energy. Eaton also tested 1200 amp circuit breakers at 9000 amps of fault current at 480 volts. First, let's take a look at the test performed on a 1200 amp molded case circuit breaker set to trip via its standard instantaneous function.
3, 2, 1, 0.
Next, Eaton's 1200 amp NG molded case circuit breaker with maintenance mode was tested.
3, 2, 1, 0.
Let's look at a breakdown of the results of this test. The 1200 amp circuit breaker set to trip via its standard instantaneous function cleared the fault in 45.9 milliseconds. Eaton's NG molded case circuit breaker with maintenance mode cleared the fault in 18.2 milliseconds. The arc flash energy was 1.63 calories per centimeter squared for the circuit breaker that was set to trip via standard instantaneous. Again, Eaton's molded case circuit breaker with maintenance mode outperformed with an arc flash energy of only 0.4.
The electronics does so much for the ability of the overcurrent devices that it really adds a lot of value to from an incident energy reduction, electrical safe work practices, and then the capability to communicate with these remotely. Once you have a brain in there, we can communicate out Modbus, other different types of protocols. You can open a breaker from your computer, from your cell phone. It's password protected. You can download settings and upload settings, and there's just so many things that you can do to get the electrical worker outside of in front of a piece of equipment. And then the other big progress from a molded case circuit breaker perspective was the invention of the AFCI circuit breaker, which detects arcing and sparking. We put a small microprocessor right down in the middle of this device, and we can tell it when to open. We can detect series and parallel arcing. I did a session on AFCIs last week, and we can recognize the high current arcs that'll cause fires and the low current arcs that'll cause fires. We had people protection in there and equipment level protection in there. So there's so many different things that we can do to help us with the understanding and providing value from a molded case circuit breaker perspective. All right. It is 2:00. I promised 2 hours, and I gave you 2 hours. And we have an exit, a little exit interview thing. And while I have that up, I am going to take a look at Mentimeter, or not Mentimeter. I'm going to take a look at the chats here. So what do the chats say? Take a look at chats. Not chads, chats. UL Mark, you know what? There's another. I'm going to leave that up, but there is a document that you can reference, and it's I don't know, Jeff Fecteau, you're on the line. You may be able to tell us more if this is still out there. I googled this and I found it. I'm not sure how to find it, but if you have a link direct that you can put in the chats or whatnot, there is a UL marking guide, and they have various marking and application guides. And what this reference does, I have already the link on my YouTube site down below in the descriptions, but it shows you exactly what all of the markings that you'll have on a breaker, the interrupting ratings, the terminations, separately shipped conductors, adjustable trips, what the class CTL, the delta, what that means when it's marked a delta. There are so many things. I mean, I could spend a whole week talking about circuit breakers. We just touched the envelope. I think my hope was to give everybody some really good basics to help you understand some of the fundamentals as you move into the proper application of breakers, it can be a lot more complex and complicated. But this guide gives you all of the different, I'm just going to search down, it shows all the different listing marks that you could have. There's the classified mark I talked about. Hey, thanks, Ryan. I just saw you come in on Facebook. I don't know if I was actually live streaming on Facebook or not, but in any case, Ampere ratings, line and load identifications. Remember, if a breaker is marked line and load, then you can't reverse power feed through it. For those of you who need that Menti code, 45, 60, and 77, go to menti.com and 45, 60, and 77. That's what's going to give you your exit. And what I do is I compare the intro to the exit. You really want to be in both of those. If you don't get a thing and if you don't get a certificate and you think you deserved one, send me an email, please. But this is a great resource for you online. Just Google molded case circuit breaker marking guides. And div Q, the performance of which may be affected by 4 degrees C ambient temperature. Thanks, Jeff Ecto, for chiming in, buddy. UL on the house, y'all. Motor circuit protector, an example of an instantaneous trip breaker. Yeah, motor circuit protectors, that's an instantaneous only breaker. There's no thermal capability in that. Is that the same as a 30-second withstand with regard to holding the contacts together longer? That's true. So if I have a big power breaker that has a 30 millisecond withstand, I'll hold those contacts together for 30 seconds. Oh, hold on. You guys online, you're not seeing what I'm showing. I'm not showing what you're seeing. Let me get that marking guide back up. I was scrolling through it and nobody online could see it. I don't know what happened to it. Let's do this. What I'm going to do. I'm going to show you how I found, here it is. I'm going to show you how to find that. If you go to, if I just Google molded case circuit breaker marking guide UL. And you'll download a document. You open it up. You notice I opened it up 3 times so far. And it opens somewhere on your computer. There it is. And this is the molded case circuit breaker marking guide. This is from 2016, but you know, breakers haven't changed much since 2016. But this tells you all of the markings, tells you what everything is required. So this is a really good, it's a good read. It's a free download. Just Google it, you'll find it. I put a link to it on my YouTube underneath this presentation. Remember, my YouTube thing will be up there for a while. I mean, I'm not planning on taking it down, so you can watch it whenever you want to. It tells you all of the breakers markings, anything that's a test function, trip level markings. So there's a lot of good information, and it helps you understand what those markings mean. So, and all of the different ratings. So it's a good reference for you. Again, all I do is I just Google it. I have it saved on my hard drive, but I just wanted to show you how to get to that. All right. So hopefully that helps a little bit. There's your code. And I'm going to just continue to go down through this. I'm not sure how many people I still have on YouTube. I'm just going to minimize, see who I got out there. 310 on YouTube. Thank you for showing up. Thanks for watching. I don't know what I've got going on Facebook. That's the first time I've ever been working on Facebook, so I don't know what's going on over there. I haven't been watching it. I don't know if I have people commenting or not. I'm sorry on Facebook if you're there and you're asking questions. I'm just not that familiar with the live stream on Facebook yet. You're not committing to share your slides. Is the information on slides proprietary property of Eden? As far as I know, I had multiple people ask me to share my slide material. My problem is I have a lot of slides. I've shared them with various organizations and things of that nature. It's just really hard to get these things off of my computer. I have a hard time even transferring them to other Eaton people. I try to mirror my stuff on internal network drives. So I'm hoping that the YouTube video has a lot of the information that you're looking for. If you're a trainer, an educator, please send me a separate email. Especially like if you're an IBW Training Alliance group or an independent electrical contractor kind of guy, let me know. I'll do anything I can to help. And I, and we have people that'll do education across the country as well from an Eaton perspective. I'm just looking through some of the chats here. What are the major differences between molded case? I already did that one, so I've gone back too far. Audio is great. Thanks, Nihad. I hear you just fine. I remember when that was going on. I remember Don Ganier's question. I remember the Gunter's West question. For one brand of breakers, a piece of solid wire or a screw and a nut works much better than their identified handle tie. Ouch! The identified handle tie lets you turn off one of the two breakers without turning off the other one, if you try. Well, and that's the intent of that handle tie, Dawn. You're right. You need to have that on both of those handles because you want to take them both off. Handle ties do not create common trip. That is correct. Thank you, Mr. Platt. Yep. No requirement to trip second breaker. That is right, but it is a requirement to open it when you open it. Yes, thank you, Bradley. There's a eaton.com. I'm going to put that up here on my YouTube. So www.eaton.com/services. We have a complete services division that will do your studies for you, help you do your set points, all that good stuff. Saying when you manually turn off, okay, now I got an argument going on chat. I love this stuff. Trip free means that the breaker will trip even if the switch is held in the on position. Yes, James, that is true. If you hold that breaker on the on position, it's still going to open when it's listed, when it says trip free like that, when you have that topic of trip free. That's exactly right. Handle locks will not interfere. So if you have a handle lock and you put a handle lock on it and you're locking it, then it trips, it's still going to trip. Yes, above there interrupting in St. Louis factory. Very impressive to see. Yeah, so, and we have a free class we do for consultants and contractors. Thanks again, Tom. I sent you a couple notes about the slides in your Facebook Messenger. Great, thank you, Ryan. So I go out if you sign up for one of our classes that we offer in our busman group, you can actually go down. I think you just have to get there. We feed you, we put you in a hotel, and then we teach you about overcurrent protective devices. We blow up some stuff in the lab, which is really cool. We do the cable whip test. We blow up a fuse. We cause a little arc flash event. And what I like about it is they show you, here's what you're not supposed to have, and then here's the way it's supposed to work. So they tell you they show you the bad, but they also show you the good. X to R rating 6.6 for testing breakers may be different than the power system X to R ratio. That is correct. And it'll be different. You just don't want to have an X to R ratio greater than 6.6, which is really hard. Really hard. I say that because it happened to me once. And I was doing a system, I missed it, but that's okay. You keep the hacker on the breakers for us old guys who remember when that was a code requirement. Yes, that's a memory. It's just, oh, what a memory. All right. HVAC equipment label still not fused or hacker. Tom, sorry, but I need to cut out early. That's okay, Jeff. Thank you, sir. Ron, he did presentation on you. Yep. Everything is up on YouTube. Thanks, Eddie. Thanks for the feedback on the session. A lot of people are asking for slides. Remember, this is on YouTube. Go to all of my stuff. This is on www.youtube.com/c/Thomas Domitrovich, and I'm saying that for the WebEx guys and gals. The people on YouTube, I don't need to tell you it's on YouTube because you're on YouTube. All 272 of you still hanging in there. And the Facebook guys and gals, I don't know what's going on over there. But in any case, I'm streaming over there. DivQ, DIVQ on the marking guide. Thank you, Jim, for joining us. Thanks, Mayrod. Excellent, TJ. I appreciate you timing in. 2 hours into the presentation. John Henry, what the heck? Everybody else, you should have been on YouTube, John. Thanks. Great training. Happy Easter, everybody. Happy Easter. Happy Good Friday is Good Friday. That's tomorrow. Our code training, 2020 code changes will continue on Monday. I've got a fusology, just like Breaker Basics, but all about fuses next week. I'll be posting that as well. Thanks for everybody dialing in. And let me look up on YouTube what we got going on up there. Is there an exit quiz? Yes, menti.com 45, 60, and 77. Enter that code at Menti. That's your little exit quiz. All right. See what else. The other thing. Everything is working good there. Voltage case circuit breakers. We saw our videos. Any other questions? Anything? Right. Well, we are going to, I'm just looking through the YouTube chats. Looks like there was a lot of stuff going on YouTube. All right, everybody. I am going to, I believe I am going to sign off. So I appreciate everybody tuning in on YouTube and on Facebook. There's probably a bunch of comments over there that I didn't get to, but in any case, dual streaming can be rough. Thanks for dialing in. Thanks for those on WebEx. Thanks for you on YouTube. Thanks for those on Facebook. And I am going to cue the outro. So take care. Stay safe. Happy Easter, everybody. And we'll see you next week on Monday.